Okay, so I think this is the sixth video lecture, kind of lost count, of the chapter on neurobiology, about halfway through. So this one's going to talk about the neurons, or specifically about the synapse. And this slide's just got a bunch of terms that are important, and I'll define them. And I've got some images that hopefully will make a little bit more sense. So the term is the synapse, and the synapse is the space between the dendrites and the dendrites of the one cell and the axon, or what we call the post and the pre. The synaptic cleft, that's the space. The terminal button refers to the end of the axon. The vessel is where the neurotransmitters or the chemical are inside the terminal button. Binding is the term for when the molecules attach to the next cell. Reuptake is a fancy term for when the chemicals get recycled. And then pruning is a fancy word for, and this is interesting, is actually over the course of our life, synapse, it's literally like a use it or lose it kind of thing, is that if we don't use neural connections, they will die or they will be pruned. And researchers suggest that when we're born, babies have all of these potential all these potential neurons and synapses, and only the ones that get reused are the ones that become pathways, neurological pathways. The rest are pruned. And so it helps explain things like if a child doesn't have verbal interaction, that the parts of their brain that would process language don't function or don't develop, or if certain like, I'm trying to think, cognitive processes or motor neurons or sensory neurons aren't stimulated, then those neurons effectively die. There's a term in child development called critical period, and it speaks to like this is the time that if this part of your brain is not exercised, it will die. That's what I mean by pruning, but I'm getting off track. Okay, so here's some images of those terms. This is the presynaptic cell. So this is the end. This would be the root of the tree, right? Or the axon, the end of the axon. Inside the axon, you have these vessels. You have these cases of molecules, and these molecules are different chemicals, different neurotransmitters, and I'll tell you more about some of those in a second. This one happens to be serotonin. When it is kicked out, right, when that electrical charge kicks out the neurotransmitter and it floats across the synapse or the synaptic cleft, it locks on to a receptor site at the other side, and that's what we call binding. And then it causes this electrical reaction, and it continues on. After it has either turned the key or done its business, it may let go. And in that case, it will float back up, or in some cases, it won't find a key, right? And so it'll just float around for a while, and then it will be recycled or reuptake. Reuptook, I don't ever know how to say it. But there's something called a reuptake, and that is where the molecule goes back to the original cell. Okay, so another way I sometimes describe this is you can kind of think of it as a bay, right? A bay where you put boats. And on one side of the bay, I'm going to stand on one side of the bay, and I have bananas. And a friend of mine is going to stand there, and they have avocados, right? Well, me standing there represents like the vessel, and I'm holding the neurotransmitters, which is the bananas. I throw those neurotransmitters, I throw those bananas into the bay, and they float across to the other side, and you and your friends are standing over there at the other side, and you collect all those bananas. Well, some of those bananas you're going to eat and use, right? Others bananas are just going to kind of float around, and eventually they may float back over to the other side, and I may pick them up. Well, you may decide, no, let me change that. It's me and two of my friends. We both have bananas, and we're throwing all these bananas in, right? Well, you see all these bananas coming over and decide you need to get some of your friends to come to get all these bananas. Look at all these bananas here. They're all going to be wasted. Come here, friends. We need to help get these bananas out. So me and my friends are throwing bananas in. You and your friends are picking up bananas. Well, I start to notice that there's a whole lot coming back over to the other side. So I tell my friends to stop. Just stop. Go away. We don't need any more bananas over here. You guys can just go back home. So now I'm the only one throwing in bananas. Well, now you and your friends are over to the other side, and you're starting to argue. You notice there's fewer bananas, and this is starting to make you really irritable. You're starting to get annoyed. right? And so this is kind of what happens when we become chemically dependent on something. Say an antidepressant, or maybe a drug like cocaine, or amphetamines in particular. Or I know a better example is nicotine. So we have all of this chemical happening in our brain, and our brain does not, our bodies do not waste. You notice that before we will add fat if we have extra chemicals. Our body just does not waste anything. So if it notices, well, of course it will notice when there is more of a neurochemical being processed, when there are more bananas in the synapse, the body will stop producing so much neurochemicals. Well, or it will do, or on the other side, it will develop more receptor sites. So when we have when we are introducing an external neurochemical, and I'm probably getting way ahead of myself and confusing you more, doing you more harm than good, but when we introduce a chemical that acts like a neurotransmitter, then more of these receptor sites are going to develop, or our body will quit producing it. Well, then when we withdraw it, this really works better with what is everybody addicted? The pain medicine, the pain stuff. Uh, mm, it's an exogenous endorphin that people get addicted to. Anyway, it's escaping me. Anyway, so you're dumping in all of this neurotransmitters, and there's either going to be more receptor sites, or the body is going to quit producing it. Then you take away that drug, and now I have all these receptor sites that are screaming for this chemical that you used to give me, and my body has quit producing it. So a good example is actually if you ever take an antidepressant, and they say in the beginning, like I've been on a couple of them, and it's those first few weeks that are really rough because you're introducing a new chemical to your brain, and your brain stops producing its own, or it develops more receptor sites. So there's this period where you have to reestablish some sort of equilibrium, right? So now that your friend has noticed that there's fewer bananas, then some of those people can go away, and eventually the number of bananas that are going to be thrown in are going to be the same as the number that are being picked up. And that's when you reach some sort of equilibrium, but it takes a minute. Okay, so let me talk a little bit more about this. This is a vessel. This is a vessel. These are neurotransmitters. These are the chemicals. They're floating across, and they are binding. In this case, it is serotonin, and serotonin is one that regulates mood, right? Something drugs called like Prozac and fluoxetine, I believe Lexapro is too. They are what we call SSRIs, and what an SSRI does is it blocks the reabsorption. So it's a selective serotonin reuptake inhibitor. This you can't see my finger. This right here would be the receptor site. No, that's what this one is. This is a receptor site, right? Or reuptake, right? It's because I said things get recycled. Let me use this one. This is a better example. This would be a receptor site, and what the SSRI does is it stops this. It would be as if, in my little analogy of the bananas, somebody came and said, no, you can't take those bananas. You need to throw those bananas. No, and those bananas that float back across, right? If somebody came to me and my friend who are throwing them in and says, no, you can't pick those back up. You need to throw those back over to the other side. We need to keep those molecules in the synapse. We need to keep those bananas in the bay so that somebody over there finally picks them up. Same sort of thing. This is the vessel. You got the serotonin, you got the molecules, they're floating across, and they are binding. Receptor sites are a little bit like a lock and a key, and certain molecules can bind into lots of keys. So you can have like a pass, right? You can have a pass key that opens lots of locks, but others are very specific. Other receptor sites will only bind with certain molecules. So in some cases, you can have prescription drugs or illicit drugs that can sit in certain receptor sites, so they can they're like a pass key. Okay, I'm going to stop here, and I don't want to rush through these others, and I will talk more about this particular phenomena in the next video lecture.